Hello, this is Rick again, your bike fitness coach. This is going to be a little bit longer video. It's going to be kind of in two parts. As it goes through the video, it's going to get a little more complex. So the first part is going to be more for the beginning cyclists. I've been asked by a number of people to put some general information about bearings and what these different things mean on bearings. And as we get toward the end, there's going to be some notes for the mechanics that I've discussed several things with mechanics, and there's going to be some interesting notes for mechanics to listen to and review as well. So let's get started. So for the general, on a bicycle, there's basically headset bearings. There's two, one in the top, one in the bottom. There are two wheel bearings, two rear derailleur jockey wheel bearings. There's two wheel bearings in the rear hub and two bearings in the free hub body. And most importantly, there's two bottom bracket bearings. We'll get into each of these in a little bit more detail right now. Headset bearings. As you can see, if you go through the chart here, we got the top cap area. You got A and B and C. The A would be the preload bolt. B is going to be the top cap, and C is the, actually down here, the star nut that goes into the steer tube. Again, usually for a steel steer tube, or like Cervelo does, they have a steel insert that's epoxied in that the star nut can go into, or you would use an expander plug for a carbon steer tube. And what happens is when you put the star nut or the expander plug in and you tighten down the top cap, it sucks the bearing, it sucks the whole this whole assembly together. This second part, D, E, and F. D is going to be the top cover assembly. So E would be the bearing. The bearing is basically buried inside. It takes up inside of this area here. And F is the cup itself. So there's the cup, spacers if needed when you put this whole assembly together. And then the bottom part, the G is the bottom cup. This slides into the bottom of the steer tube. And then H is the lower bearing that's inside of this lower area here. So basically this is the way a typical headset looks like, and this is a quick diagram of how it's all put together. Let's talk about the drivetrain a little bit. The first part is the crankset, front derailleur, chain, cassette, jockey wheels here inside the cage, jockey wheel here, and the rear derailleur. Interesting to note on the last chain, the chain video we did, if you notice the chain, the lower part of the chain is what really rubs and gets worn on the drivetrain. The lower part disintegrates first, if you will. If you look at the new SRAM chains, the Axis chains, they're flat on the top. That's because the top part of the chain never really touches any of the drivetrain mechanisms. Here is the bearings and the jockey wheels. Here's two types of jockey wheels. You have one that's basically pushed on Amazon and Alibaba. These are the Chinese full ceramic bearings. These are the ones you see where the person holds the bearing and they spin it real fast and it goes on for minutes. Well, the pluses are there's very low frictional resistance with the jockey wheels. The negative is that there's no seals on the bearings. You only have a mud guard. So if you get into a situation like this, you've just basically destroyed the bearing. Shimano has a different setup with these steel sleeves running inside of a little ceramic piece. So a little drop of oil here and there will keep these things virtually running forever. Shimano also has dust covers, mud guards over this. And this is a pretty robust setup. So here, this is for the Shimano setup, this is for a mountain bike setup, or this is what happens to a jockey wheel on a mountain bike. And you really don't want to be in with this type of jockey wheel in this type of environment. Many different bottom bracket standards. You have external threaded, you have press fit, different types of press fit. The important thing is that there's going to be a bearing in here and a bearing in here. In fact, here you can kind of see the dust cover that's inserted over the bearing. It's normally a 25 millimeter internal diameter bearing with a 1 millimeter cup or a 1 millimeter sleeve, which makes it into a 24 millimeter, which fits the Shimano axle on their cranksets. Here is an external threaded bottom bracket, how it fits into the frame. And again, this is going to be the non-drive side. This is going to be the drive side. Once this gets inserted, the crank goes in, at least from Shimano, from this side into this side. You put the crank arm on this side and put the chain on, basically pedals, and you're ready to ride. A rear hub assembly. So there's 4 bearings in a rear hub. You have 2 bearings in the free hub body. Note the cassette gets attached to this piece right here. Bearing here, bearing here. The axle goes through and hooks onto the outside cap. Bearing in the hub itself, there's a bearing on the outboard side and the bearing on the inboard or the outboard side and the other side. So 2 bearings support the free hub, and then you have different types of ratcheting mechanisms for the free hub to drive one direction and not the other. Assembled, here is a cassette. The free hub body is now hidden. The axle is internal here, it's hidden. You can see the rear hub and the cassette and the chain. The common bottom bracket bearing sizes are 6805, which is a 25 millimeter ID. Here is the internal diameter of a bearing. The 6806 is a 30 millimeter ID, and the new dub is a 29 millimeter ID. The OD, or outside diameter, is 37 millimeters for a 6805 or a Shimano-based crankset system, 42 for a BB30 or a 6806 bearing, and a 42 also for a dub bearing. The widths are all the same. These are the world standards right here. 6805 is 7 millimeters width. The 6806 is also 7, and the dub is 7. Some more nomenclature. You have the outer ring on a bearing. You have seals. In this case, it's 2 RS, 2 rubber seals, one in here, one here. This goes all the way around. Inner ring, outer ring. Question for you, looking at these, here's for the mechanics. Is this a contact seal or a non-contact seal? Leave your answer in the comments. Is this a contact seal or a non-contact seal? The contact seals you want to use for mountain bikes or anytime there's going to be dirt, debris, mud, water that you're going to be riding through. You want a full contact seal that's going to keep all of the dirt and debris out. A non-contact seal, there's no friction. It doesn't come into contact with the inner ring. Remember, the outer ring is stationary. It's press fit into the cup or the frame. The inner ring rotates with the crankset. with the spindle of the crank. So you want for a road bike, tri-bike, you would want a non-contact seal, a little less resistance, frictional resistance, plus you don't need all of the dirt and debris. You're usually riding on a clean road, asphalt, cement, somewhere that there's not a lot of dirt, debris to get into the bearing. More nomenclature. You have the outer race on the outer ring. You have the inner race on the inner ring. This is a little bit more detailed what the inner race looks like. It's a groove, as well as the outer race is a groove for the ball to ride in. The ball here, here's another ball down here, another ball taken out of here. You also have what they call ball retainer or a separator or a cage, that the balls are equally distanced apart and to keep them separated from banging into each other. The important parts of the bearing: ball material, ball grade, ABEC rating, race surface, how smooth the surfaces are ground and polished on bearings. The race material: are these ceramic? Are the races steel? Are they stainless steel? Are they brass, bronze, whatever? Cage type, or the separator type. They have different materials and different ways to lock in the bearings, the balls I should say. The cage material, the seals, what material the seals? Some have steel, some have rubber coated. There's all different types, seal type, and the clearance, which we'll get into next. So here's one thing for the mechanics to watch out for: is the world standard for a 6-805 bearing is 25 millimeter ID by 37 millimeter OD by 7 millimeter width. It's also known as 61805 or 60805-7. So basically, here is a exploded view of a Campy drivetrain showing the non-drive side bearing, showing the drive side bearing. The issue is that Campy has their own standard, a 25 by 37 by 6. So that's going to force you to buy a Campy bearing from Campy, or somebody that's going to have a 6 millimeter wide. If you try to put a 7 millimeter wide bearing in here, you're going to be, and when you lock this down, you're going to basically lock up the crank. It's not going to spin at all. So nice present for you for those that have the Campy Super Record 12-speed, 11-speed, the Record 12, the Chorus 12, the Record 11, Chorus 11, Potenza and Centaur 11, or the new H11. Go ahead and buy the more expensive bearing from Campy with the 6 millimeter specially built proprietary bearing. Everybody else uses the 6805 that runs Shimano type size. One last view of the bearing. This is what a typical bottom bracket or headset bearing kind of looks like. This is the exploded view. There is the inner ring with the race. Here is a different type of phenolic ball retainer where the balls get just snapped into the retainer. There's the balls. The three types of bearings that are out there: you get steel bearings, which the races, the rings, races, the balls, retainer, everything in here is steel. Example, it's what steel ball looks like: steel rings, steel balls. The next is full ceramic, or what they call ceramic. Here is silicon nitride, is usually black. Aluminum oxide is usually white. They can mix and match. You can have silicon nitride races and rings and aluminum oxide balls, or vice versa. The note is that this is a full ceramic bearing. Hybrid steel. Hybrid steel would be a steel races, rings, ball retainers with a ceramic ball, either silicon nitride or aluminum oxide. So this is called a hybrid ceramic. These are more robust than the full ceramic, especially when you talk about the loading of a bottom bracket bearing when you're cycling. Another question that has come up is that what is ball grade? What does grade mean? Because a lot of the ceramic ones you see from China are grade 3. Some of the American ones that are like high quality SKF bearings, they supply steel balls at grade 5, and these are about in the $250 range for a 6805 or 6806 bearing from SKF, but again, very high precision. What this means, a grade 3 is the roundness, how round the ball is. It's round within 3/millionths of an inch. The grade is how rough the surface is. Not only how round the ball is, but how rough the surface. This is 5.5 millionths of an inch. A grade 5 would be round within 5/millionths of an inch. There's a lot of grades between here. I pulled out the 25. The 25 is what I've read some specs on Shimano grade balls. The steel balls are about 25. Some of the cheaper 25-cent, 35-cent bearings use a 200 or greater. So there's more roundness errors and roughness errors when you're building these. So you basically want to match the ball grade to your application. There's also now ABEC. ABEC is another rating. This is very important, seems to be with skateboarders. What ABEC looks at the bearing as a whole, not just the ball. The ABEC looks at the bearing. They look at dimensional accuracy and running accuracy. They look at how accurate the bore diameter is, the outer diameter, the bearing width, the inner ring deviation, and the shape error. Axial runout, which we'll get into in a minute, and inner and outer ring runout. So these are listed as ABEC 1, 3, 5, 7, 9. There are other standards in other countries as well that use the same grading but different nomenclature. So ABEC 1 and 3 are kind of the lowest precision and efficiency bearings, usually vehicle bearings, skateboard, mechanical / bicycles. You don't need very high precision on a bicycle bottom bracket because you're not spinning the ball, you're not spinning the bearing 30,000 RPMs, you're spinning at 100, usually at the most maybe 120. So you don't see a lot, you don't need a lot of balancing of the bearings. You know, all these down here, 5, 7, 9, the 9 is going to be a perfectly balanced bearing where when you spin it, you can run it in a motor running 50,000 RPMs and it's not going to disintegrate. It's not going to bounce all over the place due to unbalancing issues. So the higher the ABEC rating, the higher precision the bearing is in general. And the ball is just the opposite. The lower the number, the higher precision the ball. So now we get into the bore diameter of bearings. So when a manufacturer picks something, normally what's shipped in the industry, if you order a 6805 bearing or a 6806 bearing for a bottom bracket, you're going to get something what they call C normal clearance. The 25, 30, 29 bore, that's going to fit into this line item here. So as you see, these are in micrometers. So you have 5 micrometers to 20 micrometers. So this is going to be important in a few minutes. You'll look at C2 has very little clearance. C5 has a lot of clearance. Just remember this table right now. You have C2, very tight clearance, very little clearance. CN, normal. C3, 4, 5, as you need more clearance for the balls in the bearing. Here's more detail on clearance. What is called, there's two clearance measurements. There's the radial runout and the axial clearance. The radial is the balls having movement up and down. The axial is how much movement the balls have left to right or in and out. How much movement? It depends on the requirements, the function, the speed, the force, etc. So again, remember that the radial is up and down, axial is left to right. Here's an example. Here's normal clearance. Normal clearance, I've separated this a little bit so you can see, but a CN bearing in a CN spec cup and spindle. Imagine this is a crank spindle coming through the middle of the bearing. You're looking at the edge of the bearing. This is the edge of the cup. This is the inside of the cup, bottom of the cup. You have the top of the bearing, the bottom of the bearing. Again, the bearings press fit into the cup on the outside. So what's able to rotate is the inside of the bearing. And as the balls rotate, they have some clearance. And again, that's spec'd by the cup and the crank spindle. Remember, the tighter the cup, the more it's going to press in the down direction. The bigger the spindle, the more it's going to push up this direction. So this is all spec'd. You want a high precisionly ground crankset, like most of the manufacturers, Shimano, SRAM, Campy, they all make highly precision. So all these specs are going to be the same crank after crank after crank. The cups are the same. So then they can spec a certain normal clearance bearing so it runs very freely and very nicely, smoothly when you're spinning the crank. Now, with that being said, there are manufacturers that kind of cheat the system. They understand all of this stuff, and this is where some of the mechanics had questions at one point in time. What if I spec a CN bearing and you provide me with a C2 cup and spindle, meaning that this is too small in the down direction, this is too small in the up direction. So basically what happens is the balls, you see there's no more clearance for the balls. They're being squeezed from an oversized spindle, meaning that if this is larger than spec'd, it's going to squish the bearing this way, and it's going to be squeezed from an undersized cup. It's going to be squeezed this direction. So you're squeezing the life out of these bearings, and these bearings have a lot of trouble spinning because there's no clearance, there's no room for the balls to run. The balls, in fact, are slightly larger than the opening between the races that they have to run. So watch out for manufacturers that do that. So here's an example which will start making more sense, is that if you look at the min and max, the min, max, etc., if they're spec'd to this, this is how much room the balls have as clearance internal, 5 to 20 micrometers. The smallest is 1 to 11, the largest is 30 to 53. So it's about 6 times larger here and almost 3 times larger at the max stage. But you look at this, this is 1/5 and this is half. So again, this would be important to note when you are speccing a bearing for like a hub where the bearing gets press fit into the internal of the hub and then the axle that comes through the hub. You want to basically have some room for the bearing to roll out. So who would do this type of thing? Let's anybody guess? DTSWISS. DTSWISS loves to sell you their bearings. So what this table shows, this would be a 6,000 bearing. This is 10 by 26 by 8. So you take the inside bore, how you use this table, you take the inside bore, which is between 6 including 10. So we got this line item. Now what they have done is they have on the bearings, here are the bearings two, and on the outside, this is the two outside bearings. They have the axle. So what they've done is that when the bearing gets press fit into the cup is undersized. So the bearing, when it gets press fit in, it's squeezed from the outside. The axle is oversized. So when you press the axle in, the axle squeezing the bearing outboard. So if you're a mechanic and you order a 6,000 bearing for a DTSWISS hub rebuild, it's more than likely not going to spin at all if it does spin. So what they've done is that you're ordering a CN bearing, normal clearance, which is normally spec'd, and what they have done to you is that they've squeezed the life out of the bearing. So the solution is order a C5 bearing. You have more room in here, and this is what they're selling. They're hoping you don't know this trick and you order the bearing from them. If you know this trick, you order a C5 bearing, a 6,000 with a C5 clearance, and you solve the problem. What type of bearings are there? So for the bicycle industry, they have decided on the deep groove balls, deep groove bearings. One of the main reasons is that the bearings can withstand a high radial load. So if you think about it, when you're pedaling, why would you need a high radial load rating on a bearing? Right here, when you're pressing down on the bearing, from about 2-ish o'clock to about 5 o'clock, this is where everybody's producing maximum power. So the bearing, you're putting a very high point load on these balls on this side of the bearing from here. Now through here, you're backing off a little bit because now you're transitioning from a push to a pull on this side of the leg. It's coming up, there's very little force on the bearing on the back side. Then you start increasing the load, high compression, high wear. One of the things to look out for is the plastic cups. As you continuously push into the bearing this way, the bearing is eventually going to start elongating the plastic cups. The bearing will eventually become loose in the cup itself. There was a couple of manufacturers years ago that basically took a plastic cup when the press fits were first coming out and they epoxied them into the frames. Well, when you wore out the cup, you were stuck. You had to get a new frame because you couldn't take the old elongated cup out of the frame. You basically destroyed the bottom bracket and you were stuck with a wobbly bearing or a new frame. Since then, they've either the bearings are included in a cup itself. A disposable cup and bearing is where most of the manufacturers have gone. When the bearing's worn out, dump it and put a new cup and bearing in and you're good to go. Deep groove seals. So we talked about this before. There's contact seals for mountain bike, gravel. There's non-contact for road, tri. The pluses on the contact, they seal out the dirt, water, mud, etc. The pluses on the non-contact, lowest rolling resistance, no seal contact. So there's no extra rolling resistance for these. The minuses are there's additional resistance due to the seal contacting the inner race. And the minus on the non-contact is does not seal out dirt, mud, etc. So if you look at this one, she's a little bit better diagram next chart. Here is the outer ring fixed. Here's a rotating inner ring. This is a contact seal. You see there's no way any dirt or debris can get in there, but you look at this is locked into the fixed ring and it's rubbing along the outer ring to prevent dirt and debris and mud to come in. Again, this is all extra friction. A non-contact is open down in this area here. Do I need a sleeve? So we talked about 2RS. So what happened originally was Shimano, you have a seal on the outside of the bearing and a seal on the inside of the bearing. So you have 1, 2, 3, 4 seals worth of extra rolling resistance. So what Shimano did years ago for the Dura-Ace, they removed the inner seal. So now you only have 2 seals. So now in theory you have half the rolling resistance for the Dura-Ace bottom bracket. The problem was, since the inside of the bearing was open to the environment or open to the inside of the bottom bracket shell, which there's drain holes, some of the sweat goes in there, so you want to still seal it, they came up with a sleeve that goes from left to right, seals the inside. So now you have the best of both worlds. You have, this is really your seal for both of the open steel bearings, and you still have the outboard seal. So you've reduced the friction rolling resistance from the seals by 50%, and you still have watertight and dust dirt proof from getting into the inside of the unsealed bearing. Anybody else, if you look at your bearings, if you have a seal on the inside, seal on the outside, no, you don't need this sleeve because you already have the bearing sealed. This is only used for bearings that don't have an inner sleeve and inner seal. So the next video, what we're going to get into, here's a preview of it. We're going to take apart a 6805 bearing. We're going to show all the parts, show where it failed, and then we're going to reassemble it. In the meantime, see if you can name all of these pieces on the bearing. So you can leave your comments in the comment section. So this is the bearing we're going to be taking apart. This is still intact. Here's the bearing that came out of this cup. What is that? What is this? What is this? And why do I need this? So with that, we're going to, here is a link I found interesting for the mechanics out there. This, if you go to NTN Global, this is a high quality Japanese bearing manufacturer. If you go to this website, you can go through the PDF file, and this shows you, they'll actually take you step by step how to choose the right bearing for any given application in the world. So if you want to have a fishing reel bearing, you go through this, it's going to eventually come out and tell you what bearing you need for the fishing reel. So if you want to get in more detail, this is a great website, great resource. Until then, it's been about a half an hour, so hopefully that answers a lot of questions about bearings, how they work, pluses and minuses, and from there, we'll see you in the next video.